Hello! In this video, we're going to prove the following theorem. Suppose G is a group and H is a subgroup of G. Then, for every element A in H, A has the same inverse element in both G and H. Now, before we get into proving this theorem, let's first remind ourselves of some things. First of all, what does it mean for G to be a group? It means that G is equipped with a binary operation and satisfies the following properties. So G is closed under the binary operation. The associative law holds. G has an identity element, E, such that for all elements A in G, A times E is equal to A, and E times A is equal to A. And also, every element of G has an inverse. And for now, we will denote the inverse of A in G as this. So then, what does it mean for H to be a subgroup of G? It means that H is a subset of G, and H is a group under the same binary operation as G. So H is closed under the binary operation. The associative law holds. H has an identity element, and in fact, we have proven that G and H have the same identity element. So E is also the identity element of H. So for all A and H, A times E is equal to A, and E times A is equal to A. And also, every element of H has an inverse. And for now, we will denote the inverse of A in H as this. So essentially, what we're being asked to prove here is, we want to prove for all A in H, the inverse of A in G is equal to the inverse of A in H. And to prove this, we're going to be using a preliminary result. We have proven that every element of a group has exactly one inverse element. So now, let's get into proving this theorem. Now, to start out the proof, let's first consider a group G with identity element E, and let's consider a subgroup H of G. Now, let's note, as we have previously shown, that the identity element of G and the identity element of H are the same. So the identity element of H must be E. And so now, let's prove for all A in H, the inverse of A in G is equal to the inverse of A in H. To do that, let's give ourselves an arbitrary element, A in H. Now, since A is an element of H, and H is a subset of G, that tells us A is an element of G. And then, by definition of a group, every element of G has an inverse. So in particular, A must have an inverse. And the inverse of A in G satisfies this property. And also, since H is a group, we know that every element of H has an inverse. So, since A is an element of H, A must have an inverse in H. And the inverse of A in H satisfies this property. Now again, since this guy is an element of H, and H is a subset of G, that tells us that the inverse of A in H also belongs to G. So what do we see here? Well, we see that the inverse of A in H satisfies the same property of what it means to be the inverse of A in G. So we see that A has two inverses in G, right? Because they're both elements of G. But A can only have one inverse in G. So that implies that the inverse of A in G must be equal to the inverse of A in H. So we have shown if A is any element of H, then the inverse of A in G is equal to the inverse of A in H. That's exactly what we wanted to prove. So this completes the proof. So what this tells us is, if we're given a group G and H is a subgroup of G, well then if we consider any element A in H, then we don't have to distinguish between the inverse of A in H and the inverse of A in G. We can just refer to the inverse of A. And we know it's going to be the inverse of A in both G and H. So yeah, that's pretty much it for this video.